Uh, hey everyone. Yeah, so first a disclaimer that this is conducted in my personal capacity and should not be construed to having any relevance to any company or entity. Okay, so just a normal disclaimer. Okay, so today I want to talk about engineering perspective to zero knowledge and its optimization. And this is the menu for today's talk. So first I want to say a cliche that optimization is important in zero knowledge. And to see why optimization is important, we need to view zero knowledge as a computing paradigm. So let's say we want to run a program on a cluster of n+1 machines. We have two ways to run that. The first is the vanilla way, which is most people use in distributed system. We need to pay n+1 multiply the execution cost on this n+1 machine. Or we can use zero knowledge to run to achieve the same results, which we need to pay a prover cost plus verification cost multiply n, because n other machine need to verify that. And zero knowledge would only be computational efficient if the total cost of vanilla computing is greater than the total cost of the zero knowledge. And so that's we get this inequality. So from this inequality, we can see that only if the execution cost minus the verification cost is large and the prover cost minus execution cost is low, then this inequality would hold. So which means we need to, and by default, when we choose zero knowledge for a computing problem, execution cost is usually already greater than the verification cost by definition. So we need to optimize the prover cost. So basically, it's basically just point out that the optimizing prover cost is the key to make zero knowledge practical. And then we want to ask the question of how to optimize it. And as everyone knows, the key to optimize any program is understand what you are programming. However, there's a key difference between the vanilla programming, which most engineers are familiar, and zero knowledge, which is in the cryptography world. Which in vanilla programming, the general concept of optimization is we want to cater to the hardware. We want to deeply understand what optimization tricks that has been implemented on the hardware layer and then leverage that. And the recent success in these years of machine learning is a great example of that. For example, the flash attention and all the other acceleration on the implementation of the transformer algorithm leads to the success of or the VLLM, which is optimizing the inference, is all follows this pattern, which basically optimizes the algorithm based on the hardware. However, in zero knowledge, there's a difference. We need to consider the proof system because there's usually a proof system sitting between the software and the hardware. And that imposes some new challenges and opportunities. In this talk, I'm going to focus on the opportunity. And to understand that, we need to first understand a key point, which is the randomness is the core of the efficiency for this type of algorithm, for this type of zero knowledge algorithm. And they are almost the full source of why zero knowledge is actually efficient compared with a normal computing. And specifically, I'm going to focus on a very commonly used technique called random linear combination in the following session. So I'm going to review some very basic building block of zero knowledge protocol, specifically talking about bulletproof, FRI, FRI, and breakdown. And then we're going to draw some commonalities from this basic building block of zero knowledge protocol and learn from it to have some optimization on the application layer. So so bulletproof, specifically I'm going to talk about the inner product argument that is used in the bulletproof. So we have, so it's probably going to be, so it's a bit technical, but its target audience is engineer, but also Yeah, but also probably is we also skip some proofs that is in the paper thing. So we focus on actually the practical part. So we have a cyclic group of prime order P, which is G, and we have three generator. G and H are vector generator inside the group. U is the element, a field element inside the cyclic group. And then the argument we want to prove is the Peterson commitment to vector A and B and a dot product between them. So we want to prove that we have the knowledge of the dot product between two vectors. And the idea of inner product argument is to fold the vectors by half recursively. So we want to say A1 and A2 are the split of the vector A, B1, B2 are the split by half of the vector B. And then C is the constant that we know, we claim that we know. And then how it is folded is by crossing. So the A prime is a new vector that is half the length of the original vector A, which is using a randomness R multiply the A1, which is the first half of the vector A, plus the inverse of the randomness multiply the A2. And then B prime is done in a similar fashion, but also crossing the term. And once we have this, the goal would be build a verifiable reduction to the subproblem in the similar form, which is the Peterson commitment to the new vector and the dot product of the new vector. And then if we can verifiably reduce the original problem to this problem, which is half of length, then we can recursively solve the subproblem. So the idea is we want to design some problems that the prover is very hard to compute if it does not have the knowledge of the dot product. And so only if it knows the both sides of the relation, it can compute the formula correctly, which can also be checked independently by the verifier. And the verifier can also, we also want to design a mechanism such that the verifier can update its own commitment and group base on its own, given the knowledge of the algorithm without trusting the prover. So it can check independently. So the idea is we also split the group base. So because we previously already split the vector, naturally we want to auto split the group base that we use to commit to this vector. And then this, and then by design of mass construction, the prover needs to compute two things, the L and R, which is kind of like also causing the term. I won't go particularly deep into that, but by construction, as long as this formula holds, basically is if the prover is honest, then this long formula should hold. And then the original claim is, we know that original claim is correct. Then we can recursively prove this equation holds. So, and then we follow exactly similar step to fold the vector to a single element, which is the base case. And then the verifier can simply compute the constant equals to two field elements multiplication, and then check the P, which the verifier itself is computing to the end, is equal to the Peterson commitment of these two elements and the dot product of these elements, which is simply multiplication. This is just from the original paper of bulletproof, and as we can see here, is basically the verifier draws some randomness and send to the prover. The prover uses that randomness to fold the vector, and in each round. This is just a full algorithm for bulletproof. And now we talk briefly about Fry, the fast Reed-Solomon code interactive oracle proof. The goal of Fry is to prove a polynomial fx of low degree with overwhelming probability. And the idea is roughly the similar. We have a Merkle hash of this polynomial, and we want to have the Reed-Solomon code of this polynomial by evaluating this polynomial on nth root of unity. So basically 1 omega squared to omega n minus 1. And the idea of splitting the polynomial is joined or inspired by fast Fourier transform, FFT. So basically we split the polynomial by the even term and odd term. By even term, I mean the even power of the term, and odd is just the power of the term is odd. And then we again use the randomness to combine combine the even term and odd term to a new polynomial. So so here we can express fx to f even x squared plus x multiply f odd x squared. And then our new polynomial is getting rid of this square term. So the new polynomial, which is half of the length of the original polynomial, is f even x plus the randomness term multiply the f odd x. So basically, as we can see here, the degree of the new polynomial is half of the original polynomial, because we basically divide all the terms powered by half. And this is the new polynomial that we want to prove low degreeness based on the original polynomial low degreeness. And then very similarly, we also want to build a verifiable reduction such that if we can prove f prime x is of low degree under the new root of unity, which we will figure out later, then fx can be proven to be low degree under the original root of unity. And then we can apply the similar techniques to recursively prove this argument. So now how do we update the root of unity? So first, intuition is the root of unity should also be half of the length, very similarly to the group base we have seen in the Bully proof, because the polynomial has been decreased to half of the length. And we want to derive it by expanding the formula. So basically, we want to derive a relationship between the, so basically, as we can see here, the power of the original polynomial is decreased by half. So we need to raise the root of unity to the power of an original polynomial, original root of unity. So based on that, we get rid of all the root of unity that is that omega to the power of 3, omega to the power of 5, etc., and only keep the root of unity that has a power of 2 as the new root of unity for this f prime x. And then we need to find the relationship between the new community value and the previous value, so that verifier can check this relationship holds through randomness. So basically, this is actually a very basic expansion of the formula. So basically, f prime omega to the power of 2i, which is the evaluation of the new polynomial at the root of unity, equals to the the even term plus the randomness multiplied the odd term, based on the definition of the new polynomial. And then we expand the even term by sum the f omega I plus f negative omega I divided by 2. That would cancel out the odd term, only keep the even term, but we add the even term twice, so we need to divide it by 2. And similarly, we use f omega I minus f negative omega I divided by 2 omega I as the order term, because that would cancel out the even term, because there's a subtraction between this polynomial, but keep the order term. However, the order term is divided. The order term, for example, 3. 3 divided by 2 is 1. So we actually get rid of the additional number. So 3 divided by 2 is 1. So here we also need to divide another omega 2 on the denominator. And then we rearrange the term. So basically, the third equality is basically rearrangement of the second equality. And yeah, so and then basically, and then the fourth equation is based on the property of the root of unity, because of the f negative omega I is exactly equal to f omega to the power of n divided by 2 plus I. This is based on the property of the root of unity. So we get this relationship. This relationship is the new committed value of the new polynomial and the previous committed value of the old polynomial. And as we can see, it is a linear relationship between the f prime and f and two evaluation point of the original value. So, and the way the verifier just need to verify this relationship holds to be convinced that the prover folds the original polynomial correctly to the new polynomial. And to check that, the verifier picks a random I between 0 to the n divided by 2 minus I that identify the 3 points and check they are collinear. And because this is a linear relationship, so these are the three points that the verifier check. And then this is one round of this folding. And once this collinearity check pass, we are convinced this specific round is correct. So we continue to the next round and by folding the polynomial again. Each round, the polynomial's degree would decrease by half, and roughly around log 2d times, where the d is the degree of the original polynomial. Then the prover, if the prover folded correctly and original committed polynomial is indeed of low degree, then we should get a constant because the polynomial, each time the degree of the polynomial decreases by half. So, and then we get a base case where the polynomial becomes constant polynomial. Verifier just simply requests this constant as a proof for the final stage so that it can understand and be convinced all the previous claim is correct. So that is Fry. And here I want to also briefly talk about breakdown, and specifically, so this is from a paper 2021, and which is based on a paper 2020. And so here I specifically talk about the polynomial commitment used in the breakdown protocol. So here basically we can view, so in the Fry, as we previously, we view the polynomial as a long vector. Here we view the polynomial as a matrix. So basically, m is the smallest square that is greater than or equal to the number of coefficients of the polynomial, which is asymptotically to the O of a square root of d, where d is the degree of the polynomial. And then we can rearrange the polynomial coefficient to a matrix, which is the large matrix in the center of this equation. And then the evaluation of u of can be expressed in this vector matrix multiplication form. This is a standard algebra, and you can do it on your own to verify it is actually correct, but it's really standard algebra. And then we conduct two tests. The first, we want to know that, and basically, in the breakdown, linear time is not a linear code, by the way. Linear time code algorithm was used to extend this each row to extend each row to a code word, which is of length n. So extend this size m row to n, and then we get this new matrix. And then the verifier wants to verify this committed matrix of that should be composed of code word is indeed close or in proximity to an actual code, linear code. So it basically want to verify this matrix is composed of rows that is actually linear code, or at least in close proximity to the linear code. And the way it does that is so basically, so before that, so the general idea of this algorithm, this breakdown algorithm is we want to convince the verifier the vector matrix multiplication is correct efficiently, and then the verifier can just compute the result of this the first vector and matrix multiplication, which is a vector, and the dot product on its own, and then the verifier can get a square root of d times complexity and message size. So basically, the way it does that, the first part, how it can be done efficiently is first it does it so with a proximity test, where the prover computes this vector matrix product as a raw message. So it actually do the computation, and then get a message of length m, then send it to the verifier. The verifier would encode, use the linear time code algorithm and get a vector of size n, and then you need to check whether this size n vector is indeed the product of this vector and matrix multiplication. The way it does that is to open random columns, like a constant number of random columns based on the security requirements of the protocol that the protocol designer needs to check the consistency between this vector, this dot product between this vector and a specific column. So you just need to open a fixed number of random columns in the matrix and then verify that. So that's proximity test. And then, so if the proximity test pass, then the verifier can be convinced that the matrix is indeed composed of rows of linear code that in the same space, subspace, right? So, and then the evaluation, then we can move to the evaluation test where we require a very similar process, but we require the prover to compute at the point. So the prover claim is standard. It wants to prove the polynomial evaluates to the value v at point u. So, and here in the evaluation test, the verifier would request the prover to compute the vector matrix multiplication, but using the actual u as the vector. Then the verifier again encode it and then open random columns to check the consistency between a dot product and encoded vector. So after that, it can be convinced the first vector and the matrix multiplication and the matrix indeed multiply to the correct message, correct code. This is based on the property of a linear code. Basically, the linear combination, a random linear combination of linear code should also be linear code. So then the verifier can just compute the dot product, the raw message, and the other half of the u, which we previously see here, which is the rightmost column, which is any other half of u, because we already very efficiently, the verifier already very efficiently understand and know that the result of the first half, the vector and matrix multiplication, and then the verifier just compute the dot product of these two vectors, and to get the value of the evaluation of the polynomial at point u. So as we previously see that we view the polynomial as a matrix, which is a 2D tensor, but in reality we want to be more efficient, because if we only view this polynomial coefficient as a 2D matrix, we only get square root of d, because we need to actually, when you do this vector matrix multiplication, you get a vector of size square root of d, roughly. And then, so the time complexity of the verifier is, and also the message size is also a square root of d. But we can view this polynomial in very different way. We can view it as a rectangle, but also a t-dimensional tensor for a different type of optimization. And by viewing it as a t-dimensional tensor, we achieve the d to the power of t 1 over t time and message size. Basically, the way we do that is we can do a recursion on dimension. So the idea is we do a very similar process as previously described, but we check it dimension by dimension. So we do the random linear combination of row on each dimension. Each time we reduce the dimension. In each recursive call, we reduce the dimension until we get to the base case, which is the matrix case. So what is the learning here? So we just go through 3 different basic building blocks of zero knowledge protocols, and we realize they are all just recursive random Nash algorithm. So for engineers, I think this is pretty engineering terms, right? We are very familiar with. It's about zero knowledge. Basically, it's a recursive randomized algorithm on cryptography groups, or not necessarily groups, but cryptography primitives. And then in IPA, for example, like in IPA, and in both IPA and FRI, and also the breakdown, we both try to build a verifiable recurrence relationship. In IPA, the verifiers keep track of the updated group base for each round. In FRI, we're checking on a random point. And in breakdown, we are trying to reduce the dimension by doing a random linear combination of each row of a matrix. And in fact, there are many other protocols actually follow exactly similar pattern, which we won't cover today. And so if we can reduce the application level problem to this, how this protocol like under the hood works, then maybe we can find some optimized way to write the application. So here I want to talk a bit about the implication on the application. So in different, so basically, this is a very general problem, which is very commonly used in neural net inference, CNN, RNN, transformers, classic machine learning algorithms, statistical methods, all involve such operation. So it looks very specific, but I think there is a general lesson that can be learned here. So imagine that we want to, for machine learning training or inference or any type of application that can be reduced to matrix multiplication problem, then on the application level, we want to prove the relationship a result matrix R equals A multiply B multiply C multiply D, etc., where A, B, C, D are some matrix. And the naive way of computing that is in the circuit would be implement that directly using like R16 or whatever, and then you can prove that in O(n) to the power of a cube, O(n) cube, right? Because or using a stressing algorithm, you can optimize it to like a smaller power. But actually, we can. But by understanding the underlying protocol, we can actually interleaving the application logic to the underlying zero knowledge protocol logic to reduce the overheads, and also optimize using the randomness to redesign the algorithm on top of it. So basically, the prover can directly compute A multiply B equals E out of circuit, E multiply C equals F out of circuit, F multiply D equals R out of circuit. So, and provide this out of circuit computation, which would be extremely very fast, as input to the circuits. So basically, if you compute like E and F, you already get that, and then you provide E and F as input to the circuits, and then inside the circuits we can implement Frivold's algorithm, which basically using the randomness to check the matrix multiplication is correct in O(n) to the power of 2. So, and also we don't need to recompute the randomness. We can reuse the randomness from anywhere. Like in the zero knowledge protocols, we already compute the Fisher-Meyers transformation to transform this interactive proof to a non-interactive proof. So we can just reuse that randomness without additional computation to achieve the result. Which in this way, we actually can compute the proof for a very large series of matrix multiplication in O(n) to the quadratic time, instead of like O(n) to the cube or a smaller term using some optimized algorithm, but it's still larger than O(n) to the power of 2 time complexity. And so draw the conclusion. So first of all, I think it's important to understand, so at least for now, because there's this zero knowledge proof system that is immature and also sitting between the software and the hardware, and also for lots of these applications, we do not build this proof system from scratch for the specific application. Instead, we usually just use other people's proof systems that is not customized or specific to the application. Then it's still important to understand deep on the lower level building block of zero knowledge proof system to optimize zero knowledge application for now. And also, it's important to think of the argument one that actually is proving, and the possibility to derive an equivalent argument to prove that can leverage the underlying properties of the protocol, like randomness, and thus significantly make the application more efficient. Yeah, that's it. Thanks.
A big round of applauses.